we will start our problem with a rectangle which has the length of 9. And inside this rectangle, we're going to inscribe a circle so that it touches the 3 sides of the rectangle, as you can see on the sketch. Now, on the bottom right corner of our rectangle, we will inscribe another small circle which touches the big circle. And let's say that this small circle has the area of pi. Now, the question is, can we somehow calculate the area of the big circle? This problem was presented to me by one of my subscribers, Andy, from Canada. So thank you, Andy, for this wonderful suggestion. And if you guys want to try this problem out for yourself, you can pause the video right now and then come back and check the solution. Alright, so let's solve this problem. So first, let's take a look at our smaller circle. This circle has the area of pi, and we know that the area of the circle equals to pi r squared. So we can say that this area equals to pi, and if we cancel pi on both sides, we will get that r squared is equal to 1, which means that the radius of this small circle is equal to 1. So let's label the center of this small circle as p, pull the radius, and let's put our value on the sketch. Now, while we are here, let's label all the remaining vertices of our rectangle as A, B, C, and D, and let's also label the point of contact between our radius and the line BC as Q. Alright, now let's have a look at our big circle. We can label its center as O, and let's also label the radius of this circle as small r. Now we're going to use one really awesome circular theorem, which is tangent of a circle theorem. This theorem states that if we pull a radius to the point of tangency, the radius will always be perpendicular to the tangent line of a circle. And we're going to use this multiple times on our sketch. First, we're going to use it on a point Q. You can see that the line PQ represents the radius and BC is a tangent to our small circle, so this means that PQ must be perpendicular to the line BC. Alright, so now let's rotate the radius of our big circle vertically down, and let's label the point of intersection as M. Of course, since the line AB represents the tangent of our big circle, this means that our radius OM must be perpendicular to the line AB. If we do this one more time, but this time rotate our radius horizontally up and also label the point of contact as, for example, N, you can notice that the angle at the point N must be a right angle once again, since the line AD represents the tangent for our big circle with the radius ON. Alright, and now finally, and for the last time, let's rotate the radius of our small circle vertically down and label the point of contact as S. Once again, since we know that the line AB is a tangent to our small circle, we know that the radius PS must be perpendicular to this line AB. Great! So, with this out of the way, let's take a look at the line MS. Since the line OM and PS are both perpendicular to the line AB, this means that both of those lines are parallel, so we can safely slide the side MS upward to the line PQ. And let's also label the point of contact with the line OM as T. Now, again, since the line OM is perpendicular to the line AB as well as the line AD, we can safely slide the radius ON downward to this newly formed line. Now, if we clear our image a little bit and take a look at the bottom length of our rectangle AB, you can see that this length AB consists out of segments NT, TP, and PQ. So, if we substitute all our values from the sketch, we can easily work through this to get that the line TP must have the length of 8 minus r. Great. So now let's go back to our sketch. And this time, let's take a look at the line PS, which is the radius of our smaller circle. Since it is parallel to the line OM, we can slide it to the left and get that the line TM must also have the length of 1. Now, you can notice that our radius OM consists out of segment OT and TM, so we can write this down as an equation. Of course, again, we will substitute our values, and we can work through this and get that the segment OT must have the length of r minus 1. Alright, so let's go back to our sketch once again, and this time let's rotate the radius of our big circle and our small circle to the point of intersection between those two circles. If we do this, we will get the straight line with the length of r plus 1. But how do we know for sure that this is a straight line? Well, we can actually use the theorem of a circle, which states that if two circles touch each other either externally or internally, then their point of contact lies on the straight line joining their centers. And as you can see, this is exactly the case on our sketch on the left. So we know for sure that the line OP must be a straight line. Alright, so now let's clear our image a little bit and let's take a look at the triangle TPO. This triangle is a right-angled triangle. We know this because the line OT is perpendicular to the line AB. And since we know that the line TP is parallel to the line AB, this means that the angle at the point T must be right angle. So, since this is a right-angled triangle, we can use the Pythagorean theorem. We can say that the sum of the legs OT squared and TP squared must be equal to the hypotenuse OP squared. And you guessed it, we're going to substitute our values from the sketch. Now we will use the formula for square of binomial to expand this, and we're going to simplify r squared on both sides of the equation as well as 1. And if we group all our terms on the left side of the equation, we will get this really nice quadratic equation. So you can solve this equation in multiple ways, but I will use my favorite way, and that is the quadratic formula. So, if we have a quadratic equation of ax squared plus bx plus c that equals to 0, we can use the following well-known quadratic formula. In our case, a will be equal to 1, b will be equal to minus 20, and c will be equal to 64. And let's implement those values into our quadratic formula. Now, let's simplify this a little bit. First, let's simplify the things underneath the square root, and if we do this, we will get the following. Since the square root of 144 is equal to 12, we can work through this and simplify with 2, and finally get that the value of our radius must be equal to 10 plus minus 6. This, of course, means that we have two possible solutions for radius. The first one is that radius is equal to 16, and the second one is that radius is equal to 4. But let's take a look at our sketch once again, and specifically at the line TP. You can see that this line equals to 8 minus r. So, if r has the value of 16, this would mean that this line will have the negative length, and that is geometrically impossible. So this means that the only possible solution for the radius is that r is equal to 4. Alright, so now it's pretty easy to find the area of our wanted red circle. The area will be equal to pi r squared, and if we substitute the value of r, we will get that the area of our red circle is equal to 16 pi squared units, and this is our solution. So I really hope you guys enjoyed this problem. If you did, do not hesitate to leave a like or subscribe to the channel for more content like this. Of course, if you found another way to solve this problem, please write it down in the comment section below, as you always do. And until next time, see you all and take care.